Welcome back to ECE 442-542. This is the next to the last class session. We will have 3 sessions remaining. We have this lecture, a lecture Wednesday, and then I'm planning a review session on Wednesday evening after the lecture. So those are our 3 times that we will meet prior to the final exam, which is, I hope, not news to anyone. It's this Friday night from 6 p.m. to 8 p.m. So don't start your weekend early. You need to make sure that you're still focused at least until 8 p.m. on Friday. Please, if you haven't yet already, I need to thank half of you. 50% have completed the teacher course evaluations. I have no clue which 50% that represents. Don't you wish I did? No, maybe not. So I have no idea who's completed what other than the tally. So 50% of you have completed those. Thank you. To the other 50%, I look forward to those being completed prior to 11:59 p.m. on Wednesday. These slides aren't really chronological. Our homework number 8, if you've been paying attention to emails or the front page of this D2L site, there is a homework 8. It's extra credit. It's not required, but I think it will help you on a problem or two for the final exam. If you know what's on homework number 8, and you might as well do it. It will provide extra credit, and it may just be a generic extra credit. It may not be extra credit for the homework. It may be course extra credit. That's what I'm thinking. So if you've already aced all the homework, you can still do this and receive extra credit for it, if that makes sense. I am trying to have some special office hours on Thursday and Friday. I realize it's the day of the final, but I will have tomorrow's office hours at 10:30. Wednesday's office hours, I believe, are still scheduled from 12:30 to 2:30. It seems like everyone's trying to put things into this last week, but I'm thinking that's still okay. The Thursday reading day, I won't be available at the normal office hours. So these special office hours are the only ones that I will have on Thursday. And Friday, I also will entertain last-minute questions. Hopefully, you won't want to be questioning everything in the course 2 hours before the final exam. But I guess you still have that option. It's not the best option, but you still have it available. Here are the definitions that I will probably be using since I get tired of writing. CTSS and DTSS, continuous time state space and discrete time state space. What I want to do today is, in a sense, review some of the material in the class via the example. We will go from continuous time state space to discrete time state space because in the state space design we need a state space representation in a discrete time form. We'll start with that, or we'll get to that point. Then we will implement full state feedback. I think we'll try to illustrate some of this with Matlab so that you can see the initial condition responses in a regulator type design. Then we will say, wait a minute, what if we want to actually command this to move to a particular position? What does the step response look like? And is it an accurate reflection of where we said to move to? If I say I'm commanding you to go to 1 centimeter and you go to 76 centimeters, might not be what you want, or 7.6 centimeters, I don't know what. We'll see where we go. And then that will lead us into how do we adjust this gain, and that's our reference input gain. And if parameters change, which they will do, and state space representations are known to be a little bit inaccurate, they're highly sensitive, actually. And for that reason, maybe we want to introduce a concept that we've been learning about in the transform domain, which is integral control. We'll try to get through all of this. And how do you introduce integral control in a state space feedback or a state space design environment. Here is the problem. And I'm going to scroll through this quickly initially, and then we'll slow down when we start getting to the questions. But here is a generic mass spring damper system. And if you've taken the earlier class, you've actually commanded this in the lab, essentially. So you have a mass, you have a spring attached to that, and in Matlab, have you seen functions that are overloaded? It means they might have many different ways of being used. Now my variables might be overloaded. So I noticed that when I was going through, but hopefully by context you will know what I'm meaning. For example, I wanted to just use K for the spring constant, and then I go, oh, K I'm using for the full state feedback gain. Then I wanted to use B for the dash pot, and then I go, wait a minute, my input matrix is B. So hopefully you'll know by context what is what, and I've tried to distinguish them with subscripts if needed, or hopefully if I caught them. But we have a spring constant, we have a dash pot, so that basically combination is like a shock absorber, and you could think of somebody walking up and doing this to your vehicle. The vehicle has some mass, and you're now injecting an input force, which is adjusted by, well, maybe your input is a displacement, and you now have a hardware gain that turns that into a force. So you have this applied force, K sub HWU, moving this mass, and I'm labeling the position and velocity with z's because I wanted to reserve x's for my state vectors. So that's sort of the reason why some of these notations might be a little odd to you. Do you remember your physics? Here's our free body diagram. This won't be on the final, but I'm just trying to sort of remind you, and if you haven't taken the 441, 541, we'll be getting into where this comes from. F sub I is the inertial force, which is mass times acceleration. And if we account for that as a force, the sum of the forces is equal to 0. We have then algebraically these forces summed up to each other, and we then have the blue forces equaling the red force. Or we have the spring force, the damping force, the inertial force, all of those equaling the applied force in the input. Here's what we have then. The inertial force plus the damping force plus the spring constant force is equal to the input force, and here's how they all are represented. And I may switch between dots and primes. But the second derivative of the position is the acceleration. I now have mass times acceleration plus b times velocity plus k times z is equal to k hardware times u, which is really just the applied force applied to this system. And this is a second order differential equation, continuous time representation. We can solve for the acceleration or the highest order derivative by simply dividing everything by capital M, the mass, and putting all the other terms on the right-hand side. And now, what I'm hoping you start feeling good about is what you've learned about all delay block diagrams translates immediately to all integrator block diagrams. Usually you learn it the other way around. You start with all integrator block diagrams and play with what we've been doing this semester, all delay block diagrams, but you can hopefully see, and you'll do this later. You may not have time to see all of this right now, but I'm just saying here it is, and you can refer to it later. But now we have a state space representation if we label the outputs of our integrators as state variables. We now have x1 is our position, x sub 2 is our velocity. We now know that the derivative of position, x1 dot, is x sub 2. And we know that the derivative of velocity, which is acceleration, is some linear combination of velocity, position, and this input force. So we create our state vector. It's two-dimensional. We have a second-order system, a simple mass spring damper system. and we end up with x dot is equal to ax plus bu. And in this case, we have our output y being our position of that mass. This is our continuous time system. Now I was hungry, so I started thinking about apples. So if you're talking about newtons, think of a small apple. Have you gone to the store recently and bought a pound of apples? How many apples are in a pound? Here I'm assuming about 5, and that apple then represents about 1 newton of force. I'm assuming my hardware force is 4,000 newtons per meter. That means, and here's my spring constant, and my spring constant, it would take 400 of those apples to depress my spring a meter. If I didn't want to depress or compress my spring a meter, maybe a half of a meter, then it'd only take 200 apples. So I can get rid of some apples if I don't have to compress my spring as much. But these are the numbers that I selected, and those are somewhat consistent with the system in the lab, physical system. And 2 kilograms, that's about a half a gallon of milk, or about a 2-liter bottle. So if you're used to carrying around a 2-liter bottle, that's the mass that we're moving with this spring, dash pod, etc. Those numbers give us this particular system, continuous time state space, and our goal is to control this digitally. That's our goal. We want to change this system's behavior with full state feedback initially. So now what do? Now's when we start taking some notes. We have this goal of controlling this system digitally. Where do we start? Your boss walks in, you just are taking your new position, and he hands this to you and he says, I need you to control this. Go with an analog controller or with a digital controller? And she says, a digital controller. Didn't you just have 442 or 542? Yes. Who was your instructor? Oh, well, maybe we better rethink this assignment. But you better not put her in that position, okay? You better just take this and run with it. So now what do? If you want to control this digitally, what is sort of your first thought? And now your boss has given you this system. Maybe they've already derived it, or maybe you were asked to derive it. Now you've gotten this far. You've found the differential equations, you've put it into a state space representation. If you're going to control it with full state feedback digitally, the first thing you're probably wanting to do is come up with a discrete time state space representation. Final exam review question, right? Here's x dot equal ax plus bu, y is equal to hx. Find a discrete time state space representation in a state space form. What's the first thing that you're going to need to do? Now what? If you want a DTSS and you have a CTSS, what do? Pardon? Pick a method. Well, we have CTSS and we want a DTSS. I'm sort of suggesting maybe the method, there's one that's maybe easier to do. You could go a few different ways. You could find the transfer function, the g of s, then find the g of z, and then take that g of z into a state space representation. This is our square dance, isn't it? We can go all the way around this 4-square set of representations. But if we want to go directly from CTSS to DTSS, which is what I'm hoping we do now, we need a zero order hold equivalent of this CTSS, don't we? Of the continuous time state space. And now you've put on your 2-year-old hat and you say, so what do we do? Pardon? Numerical integration approach. Well, you can do that. You can do it numerically, but we want the zero order hold equivalent. So we're assuming we're preceding this continuous time plant with a zero order hold. And I am suggesting that we already have formulas that will produce from A and B phi and gamma. Yes? Did everybody hear that? Do we just guess a sample period? The sample period's the right idea. We need a sample period, don't we? And that's what I'm hoping O would raise. We need a sample period if we need phi and gamma. But we don't want to guess, do we? We've taken this class. We don't have to guess, is my idea. Or I hope that that's where you're headed. So now let's select a sample period. And this could be a final exam question. How do we do that? What are we going to base this capital T on? Do we guess? If nothing else seems to suggest itself, I guess we do. But I'm hoping that we can have a little bit better thought process or a little bit better way of finding that sample period. Pardon? What's the settling time? Did they give that to you? No, maybe you need to ask, huh? Now, we could get a little bit more insight into this system if we, I hope I've done this already. Uh-oh. Somewhere in here I better have a script. Okay. So now I'm going to just do what I just did analytically in Matlab. What I did is I actually introduced the system parameters, hardware gain of 4,000, a spring constant of 400, a dashpot constant of 10, and a mass of 2. We create the system matrix A, the input matrix B, the output matrix H, and the direct feed-through matrix, all in continuous time. And we can put that into a state space object, just one object in Matlab with this SS command. And that then internally labels it as A, B, C, and D in this command. But your variables are still as defined as capital A, capital B, etc. And now I found the eigenvalues of the A matrix. Does that help? Or do you want, or do we want something else? If you feel like you're in the know, maybe you stick with your guns. Now I can't seem, okay. So we found the open loop eigenvalues. Of this continuous time state space representation. And those were at lambda 1 equal minus 2.5 plus and minus J 13.92. So minus 2.5 plus and minus J 14. Quite a bit of ringing, omega sub d, for the damping. This is going to be a fairly oscillatory mass spring damper system. Is that what we use to select our sample period, these open loop eigenvalues? Are you guys just tired, or do you just not want to answer? Pardon? We probably need to worry about the closed loop, don't we? Because the closed loop is what we're going to be eventually obtaining, and that's based on the settling time, isn't it? This will give us a settling time, but it's maybe not the desired settling time. This will give us our open loop settling time, but you need to make sure that this is not really what you want. You want the closed loop settling time to determine your sampling period, capital T. So you have to kind of think beyond this open loop eigenvalues. To select our settling time. So in this one, nobody really told us what the settling time was, so let me just tell you. Suppose that we select I got 2.5 on the brain because of that minus 2.5, so let's not do that. Let's say 1/2 of a second. That's the settling time that we want. So how do we use that to pick our capital T? Any ideas? This is a review for the final, this piece of today's lecture. We know the settling time is roughly 5 tau, 5 time constants. And that really tells us how far we are into the S-plane. That's now this 5 over sigma, where sigma is our distance into the complex S-plane. If this is our S-plane, this distance is sigma, and this distance is our damped frequency. So this is now J omega sub D. We're at minus 2.5 in the open loop up to J 14. And we have the twin downstairs. But we now know that our settling time specification is given as 0.5. And that's now equal to 5 over sigma, and this now tells us what we want the closed loop poles in the S-plane, where we would like those to be located. Those are now at 5 over 1/2, or at 10. So in the S-plane, we want to be over here at minus 10, and we started with our poles, let's say, at minus 2.5 J 14. And we want to move those with full state feedback to at least being over beyond this vertical line at minus 10. That's where we want to be. So let's just go a little bit beyond, and how much imaginary part should I use? You remember the S-plane? What's a nice zeta value? Zeta of 0.7 is nice, right? That's the 5% overshoot if we just had a pure two-pole system. And in the S-plane, a zeta of 0.7 corresponds to a 45-degree angle. So if we go a little bit beyond 10, why don't we end up at maybe minus 12 plus and minus J12? We really don't want to mess or change that imaginary piece too much. We'll pull it down a little bit, but let's now assume that we're going to be at minus 12 plus J12. That's the desired location with full state feedback. That would be if we were in the continuous time mode. And we know that our natural frequency is that distance away from the origin in the S-plane, omega sub n. For the closed loop system, then, we're saying we need to be at 12 squared plus 12 squared, which is a square root of 2 times 12, or roughly 17. That's our natural frequency. Now, how fast do we sample? Again, we're trying to find capital T, a sample period, and we've based that on a closed loop settling time specification. Now, this is the 30 times our bandwidth. Omega sub n is our bandwidth. We want to sample 30 times that. So our omega sub s, which is 2 pi over cap t, needs to be 30 omega sub nc. Or this is now 30 times 17. And the only unknown now in that is capital T. So that capital T is now 2 pi over 30 times 17. And if you do the math, you end up with this being 0.01232. So what do you think I selected for the sampling period? 0.01. Needs to be maybe less than this. That way I err on the safer side. So now a guess would have been 10 milliseconds, right? For a sample period. Maybe. But it just happened that that's making sense, or that's validated with this analysis that we just went through. Is that clear? So now we can find capital phi, which is e to the at, and we can find gamma. So phi is our system matrix in the discrete time state space representation. Gamma is our input matrix, and that's this integral from 0 to t of e to the a mu d mu b. This is now our system matrix. In discrete time, and this is our input matrix. In discrete time. Do we want to do that now in Matlab? Just to see what we have? We already have the continuous time object, system underscore CT. On the exam, on the final, you may need to be able to calculate this matrix exponential and do this integral. and you're doing the integral term by term, and you're just using e to the a mu, you might want to pre-multiply or slide that b into the integral so that you maybe only integrate a vector instead of a square matrix. But if we let Matlab do it, we can now do the continuous to discrete command. We can say, oh, I want now my system for the discrete time to be, to be C to D, and now I just convert my continuous time via a sample period of 0.01, and it would do this by default, but I'm going to go ahead and explicitly say zero order hold for the method to do the continuous to discrete, and this will now be my zero order hold, zero order hold equivalent. There's now my system matrix for the discrete time, my input matrix, gamma, my output matrix, and my direct feed-through matrix with a sampling time of 10 milliseconds. And just for fun, I could say, well, what are the eigenvalues of the closed loop system? I can't, because I don't have access to them. They're all buried in this object. So I can pull those out. I can do another command. So I'm kind of showing you some of these commands maybe. I could say phi, gamma, h, well, I'll say it HH since I already called an H for the continuous, but it's going to be the same thing. And let me call the direct feed through as DD. And now I'm going to say my state space data from system DT. And this will now extract those matrices into defined variables that I can now manipulate. I now have my state space system matrix defined as phi. My input matrix is gamma, and those should be exactly the same as what were shown in the state space object for discrete time. I can now find my closed loop eigenvalues of the discrete time system. And these are the open loop eigenvalues, aren't they? And those are at 0.9659 plus and minus j 0.13, and you might say, well, are those even inside the unit circle? What would you expect? If I ask you yes or no, are these inside the unit circle, what would you tell me? You would say, well, compute it. But can you tell me without hitting enter? Where did we begin with the continuous time? Where were those eigenvalues of the A matrix? Where were our A matrix? Open loop. Minus 2.5 plus and minus J14. The left half plane, it was minus. We had a negative. So they better map into the unit circle. And now I can hit enter. And yes, they are inside the unit circle. Maybe not by much, 0.97, but they are stable. And there's some ringing to them because we have some imaginary part. Where are our closed loop eigenvalues going to be? Where do we want those to be? Do you remember what we set out to do? We were trying to control this with state space feedback, weren't we? Full state feedback. We know now our system matrix phi. We have our input matrix gamma. We need to find k. So we need to know where do we want these to be inside the unit circle. We know where they are open loop. We haven't yet determined where we want them to be, but do we have a way of finding them? Remember what our S values were, the desired S values? Didn't we say those were at plus or minus 12 plus and minus J12? Can you now tell me where your Z deltas are from what information you now know? Final exam question. Where are your desired closed loop pole locations in the Z plane? And now you have to remember one of the key relationships that you've learned in this class, right? Zest. I don't know, except I didn't pronounce the equality sign, did I? Z is equal to e to the st. Is that still a soap? Zest. Zestfully clean. I think that was the commercial. So now, sorry, that was in my notes. No. Now we can find Z. We now know that Z delta is equal to e to the minus 12 plus J12 times our sample period. Boy, that's a big dot above. And this ends up being 0.8805 plus and minus J 0.1062. That's where we want our closed loop dynamics to be located. And now do you know how to do that problem by hand on the final? Can you find the K matrix if you're given phi? Now what you're wanting to do is you need to have phi, let's say closed loop is equal to phi minus gamma K. And you want to find K. You know phi, you know gamma. Now, you can solve for K. You create a desired polynomial with these Z deltas, and you equate that with the eigenvalues of this. Meaning you now would say, oh, I have Z minus 0. Whatever it was, 8805 squared plus 0.062 squared, and I set that equal to the eigenvalues of Zi minus phi sub c, which is the quantity gamma or phi minus gamma k. And the only unknown in that expression now are your k's. You just equate coefficients in that set of equations. For this problem, you'll have a second order z squared plus something z plus something, and on the right you'll have a z squared with k's floating around in the different coefficients. You equate the coefficients and you can solve for the k's. If you were fortunate enough to have Matlab on the final, you could just use it, right? But we can't, but I'll just do it today so that we can kind of walk through this. We now have our desired poles, P desired, are at 0.8805 plus J times 0.1062, and then we need its twin down below. And do you remember what command we use now? Now we can find the gain, the full state feedback gain matrix with the place function. We use phi, we use gamma, so we use the system matrix phi, we use the input matrix gamma and we specify where we wanted those poles to be. And that's now our full state feedback gain matrix. A 0.0312 and 0.0086. Now what do we do? Well, we could check to make sure that that's the correct feedback gain by computing the closed loop system matrix, phi closed loop, and that's going to be phi minus gamma times k. And that is where we wanted, 0.8805 plus and minus j.1. Now let's just see what this looks like. Let's create this closed loop system object. Let's maybe create the, did I create already the discrete time system? I don't think I, oh yes, that was system underscore discrete time, wasn't it, with C to D. Now let me create another discrete time. Now this is the closed loop. This is now state space, phi C, that's my closed loop system matrix. The input matrix is the same, gamma. My H matrix was HH, I believe, and my input matrix is DD, and this was at a sampling period of 0.01. So this is my closed loop, discrete time, state space representation. Let's now see how that dynamically compares to the open loop. And to do that, let's just introduce an initial condition. Let's say that we displace mass by 1 centimeter, 0.01, and don't have any velocity, and we just let it go. So we move it a centimeter and we let it go and we see how it decays. Here's our initial condition. And this might help you with some of your simulations or Matlab on homework number 8. So now we want to do a linear simulation, open loop, and that was now system discrete time. Whoops, I need to tell it some times and input values. So let's simulate this for 3 seconds. And I don't want to see all those points, but there's, I think, 301 of those if I've now introduced my sample period. I don't want to initially apply any input. So let me just make my input be 0 times t. And now I can do the open loop response. I have my discrete time system with the input, the time, and the initial condition. And I can also look at the discrete or the closed loop. So this was system discrete time closed loop UTX0. So let me plot that. I'm going to compare those two. I'm going to plot time or the output response versus time. And that's now my open loop response. And I'm starting from 1 centimeter, and it rings for a while, which is what we anticipated, and it does settle in about 2 seconds. And we wanted to change that to where it settled in 1/2 of a second, the closed loop. So we moved our mass 1 centimeter, we let it go, and this is what it does without any control. This is our open loop behavior. Let's now compare that. So I'll hold that figure, and I will now plot the closed loop in red against that. And that's now my response of the closed loop. And is it meeting our spec? Looks like it's settling within 1/2 of a second, doesn't it? And we don't have much overshoot. So it looks like we're getting the behavior that we want in terms of the regulator response. Here we're just saying, give us an initial condition and we'll damp that out with the appropriate dynamics given by this full state feedback gain matrix. What have we done? We've measured position, we've measured velocity. We've scaled those up and injected those back into the system to change the dynamic behavior from blue to red. So this is now, if I wanted to label that, I could say that the open loop was blue and the closed loop was red. So now I have a way of reminding myself of what we had. But maybe I'm interested in more than simply initial condition responses. I maybe want to command this mass to move. I don't want to just always have to worry about somebody kicking it and then it shakes in the right way. I want to move it. I want to command it to go. So I now want to inject a reference command, which means what? Well, maybe if I looked at that, maybe you would have more interest in what we do subsequently. So let's just command this to go. Did I say how big the input was? What am I looking for? Oh, I want my input commands, or the Y. So U is 301 and T is 301. So let me now apply a reference signal of 1 centimeter of the same number of points as I have my time chopped up into. This is now my reference input command. And what I want to do is now look at the output due to the ref in the closed loop. So what do I do here? I have my discrete time closed loop system, don't I? So now I can just do the reference command with T, and I don't want to have it displaced by 1 centimeter and then command it to go there. That's basically not going to push it anywhere, and I'll just be flat, probably. So let me start at 0 and say go to 1 centimeter and see what it does. I don't want to see that data points, but this is now my, not step, but let me say a constant input response. Now, what did I command it to do? I said go to 1 centimeter, which is 0.01. I put in a reference command of 1 centimeter, 0.01. Where did it go? Almost 8 times that, didn't it? It went to 0.076, let's say. Ouch. So it's not moving quite the way I want it to in terms of my error. Now do you believe me when I say maybe we want to do something to get zero or a more accurate tracking of a constant input? I haven't yet modified this system to make that happen. I would like no error with a constant input. Right now my error is huge, isn't it? Because my y steady state was 0.076 for an input of ref equals 0.01. But I didn't really design for a command input. I just designed to change the system dynamics with full state feedback. That changes my DC gain level in my system. So now I need to introduce a gain on my reference input so that I can adjust that to make my behavior the way I want it to behave. So I want to introduce a scaling factor on the reference input. So that now I want my input to not only be a full state feedback minus kx of n, that gives me my regulator, that changes my dynamics, that gives me a phi sub c or a closed loop system matrix, but I also want to allow for some adjustment between a reference input command of 1 centimeter and where I actually end up. Because right now I inject a 1 centimeter value and I go to 7.6. Well, you could say, well, I'll just do the calculation in my head. I'll reduce it by 7.6 and just put that in if I want to go to 1. Yeah, you could do that, but then you'd have to calculate that every time. Why don't we calculate it once? So now let's see what we can do to determine this capital N sub 1. And what are the dimensions on N sub 1? How big is that? It's a matrix. How many inputs did we have? What was U? We were applying a force, just one force, weren't we? We had a scalar input. And now our reference signal is 1. So we're applying R is a 1 by 1. We want that to produce a U that's 1 by 1. What's N? It's 1 by 1. It's a 1 by 1 matrix. It's a scalar. N sub 1 for a single input, single output system is a scalar. What's K? What's this matrix K? What are the dimensions on K? it has to be such that you end up with this product giving you a scalar, don't you? You want it to be a 1 by 1 when it's multiplied by your state vector x. And x was 2 by 1. K needs to be 1 by 2. That's what we already found it to be. So now let's figure out what we can do, or how we can maybe find capital N sub 1, which is this scalar. We know our system dynamics, x sub n plus 1, in general, are phi x sub n plus gamma times this input u of n, which is minus k x of n plus n sub 1 r of n. And now the beauty of state space is your system could be a hundredth order. Phi could be 100 by 100, and these equations are still okay. You could have 5 inputs. Little u could be 5 by 1, and it now has to account for that behavior. The K matrix then would be 5 by 100. You would have 5 inputs that are weighted by 100, or you're weighting your 100 state vector 5 different ways to give you 5 rows in K. But that's not what we have in our example, but these formulas are valid for whatever your system is, however many inputs and however many outputs. That's the nice thing about state space. Now what do we do? Let's combine our equations or matrices that scale or pre-multiply our state vector. We have our open loop system matrix phi, and we have minus gamma k, and then we have plus gamma n sub 1 r of n. And I might, just to reduce some of the writing, I might call that my closed loop system matrix phi sub c, which is phi minus gamma k. And my output equation is h x of n. What we want to do now is find the transfer function between our reference signal r and the output y. In a sense, this is another review, isn't it? You should be able to do this for the final. If we z transform the output equation, we have y of z is equal to h x of z. And now if we z transform the dynamics, the closed loop dynamics, I now have, if I could do this, I'll try to do it very, I have z times x of z is equal to phi sub c x of z plus gamma n1 r of z. Is that clear? I've just z transformed that state space dynamic equation up above, and knowing that z represents a advance of 1 sample period. I can introduce my placeholder identity matrix here if I want, and I can now say that zi minus phi sub c x of z is equal to gamma n sub 1 r of z. Or x of z now is equal to zi minus phi, that inverse, gamma n1 r of z. And this capital X of z I can apply in the very first equation to find an equation for y of z in terms of R of z, and that will give me my transfer function between the reference input and the output. So that now I have y of z is equal to h times x of z, but x of z is zi minus phi inverse gamma n sub 1 R of z. So that this is my desired closed loop transfer function, capital T sub c of z, the transfer function between my reference input R and my output y. And I did all of this to do what? I'm trying to figure out what that scalar is, n sub 1, so that if I inject 2 centimeters, I go to 2 centimeters. If I inject a half of a centimeter, I'm going to go to a half of a centimeter. What does that imply I want to have happen with this transfer function, T sub c of z? You want T sub c of z to be 1 all the time? No dynamics? Sort of baiting you here. We want to select n sub 1 That's what I thought said. We can't do that, right? T sub c is representing our dynamic behavior, but we're injecting a constant, and we want to eventually end up at that constant. So now we want our DC gain to be 1, don't we? We want this transfer function, T sub c of z, at DC to be 1. Meaning, I inject a constant, that's a DC waveform. I want the output to be exactly the same. I want the DC gain of my system to be 1. So that when I put in 2, I go to 2. If I put in a half, I go to a half. The dynamics I've already set by the selection of the full state feedback gain matrix K. I'm happy with the dynamics. I now want to pick capital N sub 1, which is just a scalar, a 1-by-1 matrix, to make T sub c of z at DC, and remember what that is? That's when we evaluate this guy at z equal to 1, we want that to equal 1. Only at one frequency, at DC, and the others are behaving the way we want it to behave. Is that okay? That's maybe what you meant, but I was trying to make a point. Okay? Is that clear? So if we want 0 error due to a constant, and we have this flexibility, then we would pick n sub 1 to give us a DC gain of this closed loop transfer function between the reference input and the output. We want that to be equal to 1. What is T sub c of z at 1? Well, if I slide back up, ooh, I can't do it quite enough. But do you see what happens? Now I just have the identity minus phi, and make that inverse, so that I now have h I minus phi sub c inverse gamma n sub 1 equal to 1. That's what I'm wanting to do. H is a 1/2. This matrix inverse is a 2/2, and gamma is a 2/1. When I end up combining all of these, and these are already known quantities, this is a scalar for a single input, single output system. If I do that computation, which isn't that bad, I just have to invert a 2/2 matrix. You can do that by hand. pre-multiply by h, and this one's nice, it's 1, 0, so that's just pulling off the top row of your inverse matrix. And then you multiply that row by this column and you get a number. So that now I could, since that's a scalar, I can divide by it and solve for n sub 1. N sub 1 now is just 1 over h I minus phi sub c inverse gamma. In Matlab, they have a command for that, don't they? N1 is just the DC gain of my closed loop system, because I haven't yet incorporated the n sub 1 in this closed loop system, I hope, if my memory is okay. .62, and that's consistent with where we went. When we injected 0.01, where did we go? 0.076, didn't we? Scaled it by the DC gain of our system. Whoops, N1's not that, is it? N1's the reciprocal of that. I messed up. First time. Oh well. First time for everything. Ha. So we can use Matlab and just say N1 is equal to 1 over N1. Right? We can trick Matlab. We can just say we knew what we were doing. So this is the gain that we wanted. So I labeled it right. DC gain of the original is what we calculated. Now I need to find the gain, the reference, whoops, I'll make more mistakes now. I want the reference input gain to be 0.1312. So that now I can change my gamma with this n sub 1 in my system description, in my model, and now I can make my system go wherever I want in terms of tracking constant values. I can have zero error to those commands. If I do that, I can say, well, let me call this the system discrete time with the reference change. That's now this SS of, now I've forgotten what it was, system discrete time closed loop? No. What am I trying to do? I'm building up out of my state space. So this is phi sub c. This is now my input matrix, which is gamma times N1. My output matrix is still HH. My indirect feed-through term is still 0, which I called DD. And I'm sampling at 0.01. So this is now my scaled system. And if I want, did I already put a U1? Oh no, I called it ref, didn't I? I already have a reference command, don't I? So let me just go ahead and say, here's my output. Got in the wrong window. There's too many windows in Matlab. Yref is now going to be LSIM with this system with the Matlab's making interesting noises, isn't it? It's trying to tell me not to make any more mistakes. But here is my system model. I can now command that to go to a 1 centimeter location over the same time horizon, so that this is now my, let's say, response to constant with reference input adjust. And now what happens? Did I get what I wanted? I said go to 0.01, go to 1 centimeter, and did I go there? Now I did, and before, without this capital N sub 1 adjustment, I went to 0.076, didn't I? Now I've accommodated my system to where I won't have any errors if, and here's the big if I know my system exactly. If I know exactly what my spring constant is, if I know exactly what my dash pot is, if I know exactly what my hardware gain is, if I know exactly what my mass is, do you think that's reasonable? We're skeptics, aren't we? We're engineers. We always question everything. So it's probably not going to be always that way. Our model is probably not going to be exactly what the real system is. There's going to be some uncertainty. And if there's some uncertainty, then we're going to have some error. Even though we've designed this to be what we wanted, well, that's assuming that we know everything precisely. If the spring constant now is not 400, but it changes by 10%, and now that spring is 440 newtons per meter, it takes 440 apples and not 400 to compress at 1 meter. I doubt your spring is even that long, but you get the idea. Now maybe it takes you 4 apples to compress at a centimeter. That's almost a pound of apples, isn't it? Not quite. But we now have, so now you'll go to the store and start picking up apples and weighing them. Then you start getting a sense for what we're doing in class. And the produce manager is going to come out there and go, "What are you touching all my apples for?" "I'm doing a homework assignment." "What?" "I'm just trying to find a Newton." There are no Newtons in this. The fig Newtons are in the other aisle. Right? Where were we? Trying to get ready for the final. But in reality, in real world, you're going to have some uncertainty. And these state space techniques are very sensitive to uncertainty or errors. If you have a difference in your K, a difference in your B, then you may have, and I did the simulation, I'm not going to have time to show it here, but if I changed my K by 10% and make K equal 440 and not 400, my response now to this 1 centimeter command, it actually ends up going to about 0.9 or 93% of that 1 centimeter. It's 0.009 instead of 0.01. I'm almost 10% error with just my spring being inaccurate by 10%. Your boss is upset. "I thought you took a control class. I told you to get this to 1 centimeter and it goes to 90% of that. That's too much." "Well, I didn't know the spring constant was not going to be 400. Well, you can assume that. We're getting these from who knows where. All these springs, maybe they're not all the same. One's maybe 400, the one that you went and measured, but all the others are different. So what do you do? Do you redo your resume? Say it was nice and leave and try to find another job? No, you don't hang up your hat that easy, right? You graduated from the University of Arizona. So what do you do? What did we learn earlier in this class if we wanted 0 error due to constant commands? Go back and say, what did we learn earlier in this class? How did we guarantee 0 error when we had constant inputs? What did we want our system to be? Or how did we want our system to behave? Or did we have a strategy for controlling? Integral. We used PI controllers. We had an integral in there, didn't we? We put an integral. So, next time we meet, which is Wednesday, we'll talk about introducing an integrator into this kind of a system. Then we will also, hopefully, talk about estimators, meaning if we do not have the ability to measure all of these state variables, maybe we can't measure the velocity. We can only measure the position. Well, we're going to learn how to create an estimator that will estimate all of our state variables by just using the output. We'll measure the displacement, and from that we can estimate the displacement and the velocity, and maybe other variables if our state vector was higher dimension. We'll pick up at that point on Wednesday.